Hello, I just finished a class about Runge-Kutta Method, but I don't really understand about it. So let's find my friend Edmund, who actually expert in Runge-Kutta Method. So let's check it out. Hello Edmund.
Oh, hi. Yes, Lee. Yes.
Can you explain to me about the Runge-Kutta Method?
Okay, hold on. I close my game first.
Okay, thank you.
Okay, alright. Alright. Let me explain to you. Okay.
Okay, usually let me explain to you what is the Runge-Kutta method. Okay, let us see the history of Runge-Kutta method, which is I picked from the journal by J.C. Butcher, which is it published on 1996. Okay. Tab. Okay, the history of Runge-Kutta method by J.C. Butcher, published by at Applied Numerical Mathematics, 1996. Okay, the introduction is J.C. Butcher claimed that the Siraj was completing his famous paper. This work, published in 1895, extended the approximation method of Euler to a more elaborate scheme, which was capable of greater accuracy. So the idea of the Euler was to propagate the solution of an initial value problem forward by a sequence of small time steps. Okay, let me explain more for the formula. I take the example of dy over dx equal to function xy. So the Runge-Kutta claimed that the first Euler first order yi plus 1 equal to yi plus phi h, which is the phi is equal to a1 k1, the summation of a1 k1, and then integrate each others to get the Euler first order. Okay, and then the second order, let the h be the interval between equidistant value of x. So if you need to find the x1, x2, x3, so x1 equal to x0 plus h, x2 equal to x1 plus h, same like xi equal to xi minus 1 plus h. Okay, y will forward increase delta y with the formula k1 equal to function xo yo h, and then the k2 is the function of xo plus h yo plus k1 times h, which is h, xo and yo will be the interval been given the values. Alright, and then the third order, we can see the k2 will be difference, which is the h over 2, not by h alone. And to get the k3 is equal to f xo plus h yo minus k1, and then 2 times k times h, and then we can see the delta y equal to 1 over 6 k1 plus 4k2 plus k3 times h, so we can get y1. So if we want to use the third order to get y2 is exactly the same way. And then the fourth order, okay, we can see the k2 and k3 is almost similar, just the method is just the same, the formula is just the same. And then the k4 is equal to xo plus h yo plus k3, which is it's already standardized. So the delta y equal to 1 over 6 k1 plus 2k2 plus 2k3 plus k4 times h. So this is the fourth orders, which is in more details nearly by the approximation. Okay.
So now let's proceed to the research paper, released by Kumar and colleagues, dated in 23rd March 1976, which is about the application of Runge-Kutta method for the solution of nonlinear partial differential equation. The application of Runge-Kutta method as a means of solving nonlinear partial differential equation is demonstrated with the help of specific fixed flow problem. A particular problem of this type describing the transient flow of a gas through porous media is investigated. So based on their study, the solution of nonlinear partial differential equation is feasible by the Runge-Kutta method, since it yields more accurate result than finite difference method. And according to Kumar and colleagues' paper, the horizontal transient flow of gas through porous media can be expressed by this equation. And we know that the gas law is applicable, which is PV equal to NZRT and P equal to NBM over B. So the following partial differential equation is obtained with the range of x is greater than 0 but lower than LT and LT is greater than 0, where alpha P equal to Kp over mu B and beta P equal to pi A over Z 1 minus P over Z dz over dP. And then the evolution of transient pressure at various points in space direction is solved from the equation with the following initial boundary condition, which can be shown as this. So this is the second and this is the third. So the Runge-Kutta method in this research paper. Primarily, all the Runge-Kutta method provide an approximate solution for a system of ordinary differential equation with known and initial condition, and all these methods have an algorithm of this form. So the problem at hand may be posed as a system of ordinary equation by partial discretization of equation as this equation. In example, dp over dt equal to f dt, and the last equation we will obtain p equal to this form equation. As comparison to the Runge-Kutta method in this paper, which is the finite difference method, we will have the first one is implicit, the second one is explicit, and then the Crank-Nicholson method. So for implicit method, we have this equation, and then for explicit, we will have this equation. After that, for the Crank-Nicholson method, we will have this equation. Now let's proceed to the conversion and stability and incompatibility in this paper. This is the graph of average error percentage against time, and the next graph is norm of error in pressure percentage against time, and then the percentage error in pressure against distance. As you can see in the three graphs, the below one is the legend of the graph, which is delta t, and then implicit is the black dot, and the Runge-Kutta is the inverted triangle, and the explicit is the square. As you can see, this is how the result of computer. So from all these three graphs, we can compute that. We know that in this paper we have two distinct approaches, which is the first one is Runge-Kutta method and finite difference method. However, as observed by the author, the Runge-Kutta method yields better result, and to overcome the limitation of this method, the area of irregular grid network should be investigated. So that's all. Thank you.